If someone said how to solve world hunger, a bot would say kill 10 million people. And that would be a good answer.
It is a way to solve it.
It is on.
Hi, everybody. Today, my guest is Jennifer Vail, a tribologist, meaning she studies friction. I'm really interested in this topic because one of the big issues around technology is removing friction, which I think is a bad thing for creativity and innovation. I cannot stand when tech bros tell me they want to make something seamless. I want to talk about why that's a bad idea for humanity. This is a fascinating conversation. It's very wonky, but in the best of ways, so stick around. Jennifer, thanks for coming on.
Thank you for having me.
I really appreciate it. This is a topic that matters a lot to me, and I think it's important. It's about the word friction, and it's a critically important thing in every aspect of life, and we'll talk about why it also can be a problem too. So why don't you start with the bigger picture of friction and why you decided to write what is a memoir, actually, about a scientific thing and also an emotional thing.
Yeah, so I can't say that friction was something as a kid I thought I would end up having a career in. I didn't know it was possible to be a tribologist until right before I started a PhD. But as I started the work on my PhD, I realized all of us are tribologists. We're dealing with friction all the time. It's ubiquitous, it's everywhere. And there's not that many areas of science that actually touch on everything. Friction is at the cellular level, it's in space. So there's a lot of stories to tell with friction. And the view of our evolution as a civilization can actually be seen through the lens of friction and how we have evolved to understand it and how that's led to progress. So the memoir came about sort of naturally with friction telling its story to me and me realizing it was interesting enough to other people that we should put this on paper and talk about it.
So tribology, explain, or tribology, however you pronounce it, explain what that is for people. It is the study of friction.
Friction.
Right.
Yes, it's the science of interacting surfaces and relative motion. So we're looking at friction, wear, and lubrication specifically. And, it's if it's a word you haven't heard before, join the club. It's a
Mhm.
fun buzzword of the day. It isn't that old as a field of formalized science. It's actually
Uh-huh.
almost exactly 60 years from today. March 9th, 1966 is when that term was coined.
Mhm.
And it was
By whom?
because
By
it
whom?
was the editor of the Oxford English Dictionary proposed it.
Uh-huh.
And Peter Jost was heading up this committee that was looking into failures in manufacturing plants where the equipment was breaking, and they thought it was simply due to bad lubrication. But when they looked into it, they realized there was actually lubricant present. So there was a bigger problem happening. And as they dug into it, they realized part of it was the design of the equipment, part of it was the material selection, part of it was the wrong lubricant being used, some of it was the practice around lubrication. And they were like, oh no, this is an engineering problem, this is a chemistry problem, this is a physics problem, it's a mechanics problem. That's a whole field in itself. So they couldn't just call it lubrication, which is what they started the report as. And so Peter Jost reached out to the editor of the Oxford English Dictionary, asked for help. They came up with tribology. It's rooted in the Greek word that means to rub. So we rub things together.
You've called yourself the ambassador for friction, and you say it gets a bad rap. I know we've sort of talked about that, but what motivated you to challenge people to think about friction, even if they think about it all, because it's all around them. Walking through air is friction. Everything is friction. Sex is friction. Relationships are friction. A car is friction. Talk about what motivated you to think about it.
What motivated me to think about it as I need to start changing perspectives on it. As a tribologist, and I think any tribologist will tell you, whenever we hear the term frictionless, we get a
Mhm.
little bit, that's not quite right. Friction's there. And people would say this like frictionless was a better thing, was a good thing. And
Silicon Valley does it. We'll get to that in a minute.
so it just plays into this almost naturally bad reputation friction has. The definition of friction has resistance in it. In school, you're always told, ignore friction to make it an ideal problem. And I just realized how much we have this bias against it and don't realize how necessary it is, that it's helping to keep the plates in the earth stabilized. When the friction slips, we have an earthquake, that you're able to drive because of it. There's all these positives with friction. It's around us all the time. we don't necessarily appreciate it. As a tribologist, you start to see it everywhere and appreciate it. And so I just figured if I see it everywhere, so should you.
So should you. And you're giving it a good rap. I agree with you. This is why I loved your book. So a lot of us learned about friction in high school physics. I only took a semester of that. We're showed an inclined plane and then given formulas that either ignore friction, as you said, or treat it as the coefficient of friction as a fixed constant. My son, who is a mechanical engineer, talks about this all the time with me, and I sit and stare at him. In reality, there are multiple kinds of friction, of course. Talk about how friction behaves in the real world and why it's much more complicated than the simplified models we're taught in school.
Yeah, there's one of the many misconceptions of friction, I feel like a broken record with it, is that it's a material property, that it's just something inherent to the material. If I'm, writing with a pencil, people will think that the friction is just due to the lead in the pencil. It's actually the whole system that we're
Hmm.
looking at. It's the friction between the pencil and the paper. So both of those things play into friction. And so we've actually had to do a lot of debunking and reframing how people think about friction because for a very long time, they thought it was a constant that I'll select this material and I'll go ahead and have an expected value of friction, which is not the case. It's more complicated than that. In many ways, we can simplify friction, but you do have to take in the entire system. You can't just isolate the box. I need to
Hmm.
know the box and the floor.
Hmm.
And if you've ever had to push a heavy box on the floor, like when you first start pushing, you sometimes almost face plant because all of a sudden it gives
Hmm.
and it's much easier. That's something called static friction. So when something sits for a while, it has the opportunity to get more sticky with the contact, get more adhesive bonds. And so you actually have to use more force to break
With the
those.
floor. Right.
Yes,
And then
exactly, with the
suddenly
system.
it undoes.
And
Yeah.
then you'll break those forces and you still have friction, but it's less. And
Mhm.
so that would be, we would call that dynamic friction. So you have two types of friction there that you have to think about. So if you're trying to study friction in a system, you have to look at that startup. A lot of my career as a tribologist has been focused specifically on that static friction. When I start up a car, how much oomph do I need to overcome the friction to get everything going? That sometimes is the most important part that maybe people don't think about. And there's different mechanisms behind it. There's the friction involved with solid on solid, solid with, fluid. We all know the tricks: add water, add grease to try to make things more slippery. That changes the friction of your system and how you might want to calculate it. And then, of course, moving through air and through water, like ships and planes, drag a totally different type of friction to consider.
Right. So what are some of the common sense beliefs that are wrong?
Well, the main one is that friction's bad. Friction is just there, right? We just need to deal with it. We can manipulate it. Sometimes people think because it's there, we don't have a choice. But there are ways that we can either make more of it if we need it, or we can have less of it, depending what we're trying to do.
Mhm.
And they sometimes will think that it's 100% just make things rougher, but sometimes rougher surface can actually help us reduce friction. So it's not a one size fits all. I would say friction is one of these things where there's always some sort of exception, even when we talk about our laws of friction. One of the ones that people will cite is that it's independent of the speed you're moving something, but that one gets broken all the time. So there you can't lump friction into one thing other than it's the force resisting motion between bodies, but that's about all we can do. You can't make a stereotype around it beyond that.
Right, right. The bad rap, as you noted. So, one of the themes you come back to in the book is the idea that friction has been one of the hidden engines of civilization, actually, and that understanding it could lead to even more breakthroughs. To control fire, for example, humans had to learn how to generate heat through friction. To make a wheel useful, they had to balance high friction at the ground for traction with low friction at the axle. And ancient shipbuilders were engineering boats to deal with, as you said, drag friction in water. Talk about your favorite moments in history where mastering friction was a breakthrough that enabled a transformative innovation.
I think for me, when I was going through this book, I was surprised at all of the different examples throughout history of where we've been manipulating friction, whether we fully understood what we were doing or not. There was with the Roman chariots, they were greasing their axles, but I think it was Pliny who noted there was a note in an ancient text that said during chariot racings there was a red glow because the frictional heating could get that high. So
Mhm.
if you imagine as the person driving the chariot standing above that axle, your feet would get really warm. And what they would do for this was they would actually, after a certain distance or laps, splash water onto the chariot to cool down the frictional heating, which also keeps greases from igniting. And so I thought it was really fun that this was essentially the first pit stop that we had in
Yeah.
racing. And it
Yeah.
was a necessity because of friction, because things just got very warm.
Hmm.
And another interesting one, whether it was intentional or not, is that the Egyptians may have been using water to help optimize the friction in sand as they were moving sledges. So they found a painting that depicted, an Egyptian carrying a vase of water in front of a sledge, moving a very heavy statue. And so some
This is to build the pyramids, just for people to build the pyramids,
Yes. In
correct?
this
Okay.
in this case, the painting was moving a large statue, but it would have been applicable for pyramids too, because the last thing you want when you're moving those heavy stones is extra resistance, and moving stuff in sand is not the easiest. So researchers saw this and thought, well, they may have just been splashing water because it was part of a ritual, but actually, could that have been helping the mechanics of this whole process? And they did find that splashes of water, the way it changes how the sand is behaving, would lower the friction and make it easier for a sledge to move over it. So it may have not been intentional, may not have been why they started doing this, but they accidentally found a way to just make the friction more in their favor to move these really heavy objects around in the sand.
I was just at the Air and Space Museum, and there's a whole thing about flying, of course, which is all resistance and friction, correct?
Correct. Yes.
There was a Wright sister, for people who don't know, and the
Oh,
mother was also very I sorry, I always mention it because I'm like, "Come on." There was a sister
I
and a mother
I
who
appreciate that because even with all my research, they were never mentioned. I
well,
was
they are now at the Air and Space Museum until,
perfect.
some Trump administration official figures it out. But maybe they don't listen to this. Anyway, talk about, ball bearings. It's an underappreciated but incredibly important innovation. I mean, these are these little steel balls that are often used in all manner of mechanical things.
Yeah, they're there to give us rolling friction instead of sliding. Rolling friction will always be lower. And it's amazing because if you were to look up on the internet modern ball bearing raceway, it looks exactly like a sketch that you will find in Leonardo da Vinci's notebooks.
Mhm.
So they haven't really had to change much in their design. We had a grasp on these pretty early on. The craziest example to me came from party boats that Emperor Caligula created in a landlocked lake.
Uh-huh.
There had been rumors of shipwrecks in this. It was Lake Nemi, a volcanic crater lake,
Mhm.
for years and years and years. And finally, in 1890, divers got down there and found them and confirmed there's shipwrecks down here and they're big. So it was this whole, why are there these giant ships in this landlocked thing? Well, it turns out Caligula, who was wildly unpopular, just made giant floating party boats. And on those seemed to have some sort of rotating platform or stage. Maybe the first rotating club stage, I don't know, but they were on large bronze balls. So these were, this bizarre show of friction engineering that the Romans did to help rotate these platforms. Those were ball bearings. And then Da Vinci sketched them out. The big innovation that came with ball bearings was when we were able to manufacture the stainless steel kind and get them very uniform and smooth. But that's largely, ball bearings have stayed the same over time because when you have a good solution, you have a good solution.
Why wouldn't you go with it? So, if you ask most people what friction means, they probably picture two solids rubbing, right? Or people or anything else. Fluid friction is where things get complicated, though. When you when did people start to study understand the concepts like flow, viscosity, turbulence, and what did that unlock?
Yeah, I love where friction takes you since it's everywhere. And one of the big breakthroughs with understanding friction of fluids came from the internal friction fluids feel, which is viscosity. Isaac Newton suggested viscosity existed, that there'd be friction, friction between the layers. And if there was high friction between the layers, it would resist flow. That would be high viscosity, something like honey. That's
Mhm.
usually the example. Low friction between those layers, you flow very easily, like water. And the a nice breakthrough that came through how to measure and understand the relationship between flow and viscosity came from simultaneous work being done by a hydraulics engineer, Gottlieb Hagen, looking at how to move river water through pipes, and then I'm going to butcher his name, Poisson, who was studying blood. So you have blood and you have pipes. But at that same time, they came to the same conclusion and they determined how you could set up experiments with different pressure, different flow, and understand what viscosity was. And
Hmm.
that was just one step of the way, because there's also how fluid flows. It can be smooth or it can be turbulent. And then there's this big question of, well, if you have solids in contact, how does the fluid even get in between that contact? That's what we want to do, right? To lower friction. And so a gentleman named Osborne Reynolds is the one who figured out how to adapt lubrication theory and found the pressures in the system can cause the fluid to manage to sneak in there. I mean, we all know if water's insidious, it will go anywhere. And it actually, the fluid can have enough internal pressure to separate some of those solid contacts.
Hmm.
And that lubrication theory really set us running and understanding how we can design machinery equipment to have lower friction.
You were talking about blood flow, obviously, which is studied a lot. I happen to have what's called thick blood, and that's one of the reasons for my stroke was because the thickness of the blood, the viscosity was high. Is that correct? That it was or low?
Yeah, so
Low.
high, if you had thicker blood, I would imagine it would be higher viscosity.
Mhm.
So not flowing as easily, higher resistance
Right.
to flow. Yes.
Right, exactly, and it can cause real problems in health if
Yes.
that's the case. If people don't drink enough water, for example, it happens. You can get very sick, and it
Hmm.
affects your blood.
Yes.
Absolutely. And you can be born that way, which is interesting. The Industrial Revolution wouldn't have happened without if scientists and engineers hadn't figured out how to stop metals from destroying each other, because a lot of the Industrial Revolution is metal upon metal. We learn about the advances in iron production, steam engines, machine tools, and factories. The unsung heroes of the Industrial Revolution was lubrication that kept the shafts, bearings, and gears alive long enough to run continuously, because if not, they'd wear each other out, right?
Yeah, so when we get into lubrication, it gets complicated fast. So what a lubricant can do, obviously the goal is to completely separate those solid contacts. If you
Two
look at,
metals, for example.
yes, our two metals. If you look at the surface of those metals, even if they seem smooth and you start zooming in, you notice that the surface of the metals, they're going to have hills and valleys. That's just
Right,
how
that you
surfaces
can't
are.
see.
And the contact will be at the high points between the surfaces. So we want the lubricant to get in between there to separate them. If you put too little lubricant in there, you might just have dots of it around, but it's not really separating those high points on the contacts. So you're still dealing with the high friction of the metal on metal contact. And you can go from not separating any of those to starting to separate them, and the friction can start to drop dramatically, which in some cases could be a problem as well
Too
because you
much.
you need to know, are
Mhm.
you going to be in the high point, the low point, and then eventually you hit the minimum where you have separated all of those out and you get your low friction that presumably you want because you want to separate your metal and metal. But if you start to put too much grease in there, you can actually start to get friction creeping back in because of the viscosity
Mhm.
of the lubricant that you're using. So
Y
there's like a sweet
anyone who's
spot.
grinded a gear knows that, who drives a
Yes.
shift car. I drive shift cars. I don't think anyone does anymore, but I'm an old person, and I'm quite good at it. I drive them in San Francisco, so
Oh,
that's
wow.
yeah, I know, I'm good at
Well
it.
done.
But anyone who's had that happen can understand that, who's ever
Yes.
used any kind of gear mechanism in a car, which we don't do anymore, really. But it's still existing, it's just the car is doing it itself on automatic,
Uh, and it can get very complicated with an
yes.
automatic having to do it, especially with start-stop systems that we have in cars now to save emissions. That's tough because if you're starting and stopping, where's the lubricant going? So they've actually, most systems now will have a separate small little pump to keep that circulating
Mhm,
so that you don't suddenly have high friction at startup again and high
mhm.
wear. Because, like you said, metal on metal is, you want to avoid that as much as possible.
Right, right. Now, in the book, you explain how friction is a massive but overlooked cause of global warming, speaking of emissions. In order to lower our carbon output, we need to get better at managing friction, correct? And you can get very dirty very quickly by not managing it correctly. You write the quote, only about 21.5% of the fuel we put in our cars is used to move them, which is incredible. I didn't realize that. Even as we moved to we changed to EVs, and that's a slow process. Friction caused rolling resistance, lubrication needs, contact wear still reduces a car's energy efficiency. Why don't we pay more attention to the energy costs caused by friction? And what would it take to significantly reduce vehicle energy usage if that's ultimately caused by friction?
It's a great question. I'm not entirely sure why friction was overlooked for so long. I think it's really because friction overall has just probably been one of the most underappreciated forces in our lives. As we're getting more and more awareness of it, people are tackling it. And even just from the start of my career to now, I have seen so many more tribology labs show up in industry that never existed before.
Hmm.
And, it sometimes is unglamorous, which might be another thing. We
Yeah,
might take
efficiency is not glamorous.
Yes, and sometimes, people like the design of the overall shape of the car, which does help with friction and drag, right? But if we really want to reduce and save as much energy as possible, you have to be looking at every little thing that's moving. And
Hmm.
sometimes that doesn't seem like the sexiest problem to be working on, when in fact, if you're able to reduce the friction and all of those little moving components, even 10%, it adds up. Hopefully, people have seen this because we've been making great strides in it with the fuel efficiency of internal combustion engine vehicles. These cars aren't getting any smaller and they're not
Hmm.
getting any less powerful.
Right.
All of these things mean the fuel efficiency should be dropping off quite a bit, but
Hmm.
it's not. Like, we're still making improvements, and it's because people are finally noticing friction. We have new lubricants with different viscosity to help optimize that. We have surface texturing. A lot of work has been done there. So if you change the texture of a part,
Hmm.
does it help trap that lubricant in there and get even lower friction? A lot
Right.
of actually really clever innovation going on in these small areas that people haven't really noticed, except for the fact that hopefully they're not having to put as much gas in their car as they were
Or else they're
before.
like, we got plenty of gas, so who cares, right? That's part of it, right? And of course, the other impact is rather severe. Anyone who's watched a speed skater knows or a swimmer. They're always trying to reduce friction. But one of the things that's important is thinking about friction in cars or anywhere requires systems thinking, and that's
Yes.
a more difficult because it crosses so many disciplines of what's happening. Um, every episode, we get an expert to send us a question. We have two for you. Let's hear the first one.
Hi, I'm Adam Becker, author and astrophysicist. My big question for Jennifer is, it makes sense that studying friction can lead to massive gains in energy efficiency in many different areas. But how do we know that that's actually going to lead us to use less energy, or at least, less non-renewable energy? The reason I ask is that there's this thing called Jevons paradox that says that as you increase efficiency, can actually increase the usage of relevant resources, not decrease it. We saw this in the 1800s. People got better at using coal more efficiently, and that actually led them to burn more coal, not less. And, recently we've gotten much better at getting lighting to be much more efficient, using LEDs rather than fluorescence or incandescence. But we don't use less energy on lighting than we used to. So how do we know that efficiency is really going to lead to these, massive gains in fighting the climate and energy crisis?
It's very relevant with new data centers, obviously, that we're building.
Yeah, it's a great question and a great point. Part of my answer is probably gonna be my own optimism and a little bit, um, that I think every little bit helps, and in some cases, I 100% agree. As we make things more efficient, people, you give an inch, they take a mile type thing. So that may happen. But I personally, my driving habits haven't changed. So the fact that I have a more energy efficient car means at least my usage I'm able to save. And if I can multiply that across however many people might be like me, not changing their habits, then you are still saving that chunk, and I think any little bit is worth pursuing and worth putting towards that battle. There's maybe the 20% available. Do I believe we'll be able to get all of that? Not necessarily, but I think it's an opportunity for us to start chipping away at it. But
Mhm.
I do think he makes a great point that as we
Yeah,
make things more efficient,
we have a voracious appetite
yes,
as
we always
as
want more.
so more. So even if we take Adam's point, let's assume we do want to increase energy efficiency. If excess friction is leading to massive energy losses just in the car category, what's it doing on a global scale? What are the highest leverage friction losses if you had to pick a short list of list of climate relevant friction interventions that scale. What would you prioritize first and why?
The transportation sector is the biggest offender, and then you obviously can break that into cars and planes. A surprising one is also energy generation, right? So hopefully we will move to renewable, more and more renewables, but in the meantime, even with renewables, we want wind turbines to be as efficient as possible so that what the wind that they're getting, they can most efficiently convert it to electricity, not having to deal with the friction in the motors that they're dealing with. So different ways to chip out there. I think energy production is probably one of the most surprising areas where friction is a significant factor. And you have it from traditional power plants where you have, the turbine engines, very similar engines to what's in a plane, right? And if you can make that as efficient as possible, then you have more efficient energy production. And I do think that that is an opportunity for us to be chipping away at that bigger number. I spent a chunk of my career just creating materials to actually act in between metal on metal to reduce friction. And the whole point was to make them as small and thin, as light as possible, because it's literally every single little ounce is what they're trying to save because it impacts the efficiency of those airplanes. So, amount of luggage that we bring, all of
Mhm.
that is
Yeah,
taking big impacts on our energy usage.
right. So speaking of planes, talk about winglets. These are actually making them more energy efficient. What's a winglet?
So, if you look at the tips of planes, I do this on every plane I go on because they all have something different on the tips. There's the little winglet that's arcing up. Sometimes it's a big loop, sometimes there are little forks on there. They're all different. And these are designed to optimize the airflow around the wings to maximize the lift to drag ratio so that we can minimize the drag, use, the way the air is flowing to provide more lift with the tips of the wings. I just think it's really fascinating that we don't seem to have one universal design that seems to be the best. But I think
Mhm.
that is the exclamation point on why, particularly with fluids and fluid friction, it's just complicated. It's hard to model that.
Do you sit on the wing of every plane you go on?
I
Do
maybe.
Maybe.
Yeah.
So, in the last part of the book, you start to push on unexpected territory away from engineering and physics into topics like medicine and outer space. For example, friction plays an important role in biology. Living things move, even at a molecular level. When proteins fold and unfold, they're constantly fighting internal, something called molecular friction. What creates internal friction during protein folding, and why does understanding the mechanism matter for designing therapeutics? There's a lot of activity. I just finished a CNN docuseries which includes talking about gene folding and gene editing, etc.
Yeah, I might ask your opinion or to correct me if I'm wrong in
I'm
how I'm
I'm no doctor,
misunderstanding
but
it.
I'll try from my interviews. But go ahead.
But yeah, I mean, maybe the people you spoke to can help me with this too, because it's an area that I find fascinating. And this is one of these areas where I think the question is, what role does friction play and how much does it matter? I mean, things are moving, so we know friction is there, but I don't know if we have a clear picture of how big of an influence that has. It could be that, the more friction there is, maybe that's causing too much energy to required for folding. And maybe it is a reason why sometimes the folding fails. If a
Mhm.
protein folding fails, that can lead to things like Alzheimer's and really serious diseases. So, of course, we want to understand everything that goes into the folding, but I don't think it's 100% clear the role that friction is playing in that. But we know it's moving. You have these molecular chains, the amino acids, as they're connected and start to fold and move, they're going to experience friction. And sometimes it's the friction from the turning. Sometimes it's, energy barriers that they're having to overcome in this process,
Mhm.
different mechanisms involved in that, and people are studying different types of bonds and interactions between the amino acids that might cause more or less friction.
Mhm.
But the big question is, what does that mean on the overall process? And I think we're still trying to understand that. But if we're trying to model this process to be able to predict it or target therapeutics, we need to understand the impact of every variable, and friction's one of those
Which is
variables.
why they're using AI to do so, because it
Yes.
can do it much quicker. One of the things
Yes.
that people, as much as AI gets deserved attacks for lots of different negative things, one of the positive is the ability to take drug discovery and squeeze the time and the amount of computing that is required to do so in testing, which is a big deal, meaning they can
Yes.
come up with more therapeutics, or they can eliminate therapeutics that don't work very quickly. It usually takes a long time and many, dead animals essentially, but they don't necessarily have to do it. The other part is I did a lab at Stanford that's doing something called millibots, which are tiny little,
Hmm.
they look like Fantastic Voyage, little tiny things they inject into
Yep.
people's veins, and then they will get rid of a stroke. I had a stroke myself, so that's why I visited it.
Yeah.
And previously, they still using a catheter, but catheters have friction
Hmm.
against veins are very strong. People
Yes.
don't realize how strong veins are, but the catheter can cause damage, and if it goes up into a stroke
Mm.
clot and it breaks it apart, it can keep going. And these millibots don't; they just keep going and they're manipulated by AI, magnets, and a mapping of your brain, of an individual brain. It's
Hmm.
fascinating, but
That's
friction
amazing.
is what we talked about the whole time, almost the whole time
Nice.
during the process.
Yeah. Man, I'm gonna have to look into that because
I'll send you the thing. It's a
if
lab
there's
at Stanford, but the people working on it, interestingly, are mechanical
yeah.
engineers working with scientists because it's a mechanical engineering
Yeah.
problem,
And
really,
we're
and
seeing that more and more. So my background is in mechanical engineering, and actually, my professor Greg Sawyer, who was running the tribology lab, he now runs a department of cancer engineering at the Moffitt Research Institute because he has also pivoted that way because we're seeing so much how there's mechanical engineering that we marry with the biosciences and you have amazing technology like that. And I can see why friction would do that because if you're trying to travel through our body and through veins and to target a very specific spot, if you run into too much friction or you don't quite have the flow quite right, it's not going to be able to deliver what you want. And sometimes I remember my professor, Greg Sawyer, said he would have situations where the scientist would say, oh, something like that, I don't think that's possible. But the engineer wouldn't realize that it shouldn't be possible and would just sort of design it based on the
right,
variables of engineering and it would work.
right.
So I think it's very exciting what we're seeing with the marriage of those disciplines.
Absolutely. There's it's magnets is what they use. Magnets and AI. It's really quite crazy, and it's eventually they will be able to just inject it, and then someone in Boston can run the program in Arkansas, right? And so you prevent strokes, which then leads to all kinds of medical interventions that will very save money. Is
Amazing.
really what ultimately
That's amazing.
it is amazing. One of the things that my son was working on as an intern was using hydrogen in fuel injection engines, how you could control the blasts, right? And how you do, and friction plays a huge part in that. There's all kinds of, and uses of these scenarios, of mechanical engineering scenarios are a big part of this, which is really interesting. And, of course, he has to study chemistry and physics at the same time, but it's a
Hmm.
really interesting multidisciplinary thing. Now, on the other side of the spectrum, you have astrophysics. Now, interestingly, I'm having a doctor ask you an astrophysics question. Listeners might be surprised to learn there's friction in outer space since it's a vacuum. So that in mind, let's play our second expert question.
Hello, I'm Ezekiel Emanuel. I'm a physician, a bioethicist, and a health policy expert. And I'd love to ask Jennifer the following big question. I've studied a lot of chemistry and physics and thinking about space, outer space. Friction is an interesting question. In outer space, temperatures are very low and there's big vacuums without any molecules between various areas. So there's one question that relates to the temperature. You can't have liquid lubricants because WD-40 would evaporate and freeze, so you need solid lubricants. What is a solid lubricant? But more importantly, in the vast vacuum, is there any friction? I understand there's quantum friction. I'm not sure what that means. Maybe you can explain to me what quantum friction is, but it's not two surfaces rubbing against each other. And therefore, the question is, do you need lubricants for quantum friction and overcoming quantum friction? What would that mean for space exploration? Thank you.
Um, so, okay, we'll start with temperature. And the solid lubrication. And it's not just temperature. I mean, temperature is a big one, right? You can't have it, but there's also the radiation going on out there. It is the most challenging environment we can have, but we still have satellites, we have space stations out there, things are moving. And so we do use solid lubricants. And the most common ones are it's graphite, like you use with your pencil. So you have experience, you know that graphite moves nice and smooth. There's also molybdenum disulfide, and often you have to use a combination of both because graphite actually really needs water available to it to be able to keep it lubricious. Because what happens with these solid lubricants, you're trying to have the layers of the solid lubricant transfer from the solid lubricant surface to the other surface and then lower the friction. But when graphite does that, it'll have some, I guess again, chemistry, dangling bonds. And if it
Mhm.
latches on to the wrong thing, the friction's actually going to get quite high.
Mhm.
So out in space, we don't have a lot of water. So that's when something like molybdenum disulfide, which thrives in that vacuum condition, will be able to transfer the layers. It has low energy between its layers to do that, gives us the low friction. Uh, probably the most famous solid lubricant is the most controversial one. That's Teflon, right? It seemed like a miracle product, but now we're finding it persists forever. It was not handled well by the companies making it, but that is a very famous solid lubricant. We also have, researchers all the time developing new composite materials, blending different materials to try to get the performance in these extreme conditions because you have extreme high temperatures depending where you're at, extreme low temperatures, and you have the radiation, and it's just a crazy environment that we have out there. His other question was quantum friction, which that one could be a bit controversial because technically the definition of quantum friction, it's very specific variables that you have to have set up. It has to be in a vacuum, and you have to have things that are not charged, but are polarizable. So as the electrons are floating in their cloud, you might have more on one side than the other, and it's a fake charge in there. Water is a good example. But you have these conditions on it because if you're trying to figure out if something's happening at the quantum level, you have to remove temperature or anything from the environment that might be causing it. And so what the theory of this quantum friction is as you have, quantum fluctuations, the particles jumping in and out of the quantum, are they causing drag on each other? That would be quantum friction. And some people say yes, and they think that they have measured it. Others are very adamant that this doesn't exist. There's not a consensus on it right now. It can get to be a bit of a feisty category there. And it's also one that some people are like, does it actually matter? We understand friction more on the macro scale. We understand how to work with it. Do we really need to know on the quantum scale? And I think that that's a slightly ignorant view
Mhm.
because we've had that view on other forces in the past. Van der Waals forces are a good one. And those are the forces that cause geckos. That's how they can climb up the wall and defy what seems like defy physics. So I think it's worth pursuing and understanding because we don't know what we don't know.
Right.
And
And it can tell us a lot about how planets and galaxies evolve, correct?
yes, I mean, who knows what it could tell us? We don't know
Right.
until we
Geckos,
understand it.
people.
Right.
Geckos. What
And
the f
and,
I love
we're
a
over here
gecko.
trying in labs to
Mm.
mimic exactly, geckos climbing, and that is all due to Van der Waals, which at some point people were like, "Oh, those aren't real. Who cares about that?" So, I don't know what we don't know about quantum friction or where it could take us.
Mhm.
I think it's worth pursuing, and sometimes it's worth pursuing some things because of what you discover along the way, even if
Right.
it remains inconclusive. So,
Right. Right.
that's my feelings on that, but there are other types of friction happening out in space. It's a vacuum, but it's such a dynamic place that, of course, there's a lot of friction happening.
Mhm. It's just not as apparent as it is on planet Earth, for
Yes.
example. So, last thing I want to talk about is behavioral friction, which we mentioned earlier. For example, in a more mundane way, one-click ordering on Amazon reduces so-called friction of consumer experiences when they're considering whether or not to buy a product. That's a very simple way of doing it. Tech companies obsess over how to reduce behavioral friction, but without there'd be no creativity, no innovation, no sex. What do you think about non-physical friction? When is it something to be designed out of our lives, and when is it a feature we should preserve and even add back in? The whole point of tech is to if they use the word, it's when I started to pay attention to friction in this regard. They want it frictionless. They use the word seamless. They have a service called Seamless, right? They want it to have no barriers in order to sell you more stuff, in order to get you pulled in. Algorithms are the lack of it gives you the next thing that you already wanted, right? It's all designed that way. And for my this series I'm doing, without friction, for example, chatbots that are sycophantic, no friction from the chatbot, which is always agreeing with you. Without friction, our cognitive abilities are going to get less and less, and our neuroplasticity is going to suffer. That friction creates it. But we have the whole tech industry trying desperately to get us into a frictionless environment to buy and to respond to chatbots and have relationships with chatbots. And I know it's far afield, but it's the same thing. It's the removal of friction as if it's a problem and not an asset. Can you talk about that?
Yeah, they're perfect metaphors. The physical force of friction is obviously quite different, but just like if you ignore its existence and don't fully appreciate it, you lose out on a lot. If we hadn't figured out how to work with friction in the best possible way, we wouldn't progress and move forward. And I keep saying very similar. I am worried that as we keep moving towards frictionless in the things we do, we're losing our ability to think critically and actually work through processes, which, it's exactly what you have to do with the physical friction. You have to think through the whole system and the process and really understand what you're trying to do. When you make it so easy, we lose that little bit. And the example that I tend to use is with, GPS and maps. Of
Hmm.
course, I love that. Use it in my car all the time, but people make fun of me because I also have an atlas and physical book of maps in my car.
Hmm.
And some people are like, I don't even know how to use these things
They
anymore. And
don't.
that just worries me because, what if you end up somewhere with no signal or just something happens or your battery dies? You need to be able to think your way out of that situation. And by making things frictionless, I think we're losing, like you said, some of that cognitive ability. And it's also changing behaviors in so many ways because we just expect things like this now. It should
Hmm.
be easy. I shouldn't have to do this. We see this when we're providing technical support for people doing, engineering scientific problems. They just want us to tell them what the answer is. And it's like,
Hmm.
no, I can tell you how to use your instruments to try to get that answer, but I'm not studying what you're studying. I can't give you that answer. And so we lose a lot of productivity, a lot of thinking skills, and it seeps into the organizational structure. Everyone wants, oh, we want to be frictionless, but you better have friction in companies so that someone can push back and speak up if it's not the best idea or there's another way.
Hmm.
Think creatively, like you were saying. It sort of stifles creativity if we
Right.
don't embrace the fact that friction is a good thing.
Yeah, it's an interesting thing because I've had so many arguments with tech people about this, and especially right now around chatbots, right? Where it will lead to actual cognitive problems with our society, not just loneliness, but they're trying to solve loneliness by creating frictionless partners, right? Which they love to use the word chatbots, which I think is an adorable term for what is a synthetic relationship. And
Mhm.
everyone who is in these, I'm like, there's nobody there.
Right.
There's nothing there. And it's designed to not push back. And even though this is sort of a trope, for women, they get a man who always responds to them. And this is for straight people. For a man, they get a woman who always agrees with them, right? And it creates a real problem for not just human propagation, but humanity to be able to work together, correct? When all the friction is either made hateful, which means you don't want to
Mhm.
engage in it, or the friction is not there. You are only with people in your and they, they're called silos for a reason, right? You
Right.
end up with only people who you're in violent agreement with, which to me describes Silicon Valley almost to a T, except for a couple people. Like this week, we've seen it with Anthropic saying, no, we will not be doing that. That was a human making that decision, not a bot, because when they actually queried the bots about war, for example, they all agreed we should use nuclear devices, which is, of course,
Eh,
the right answer if
yeah.
you're going for
Yes.
efficiency and lack of friction.
Right.
I remember, and this is the last thing, and I'd like you to answer this, when when I was at a dinner party, they're like, well, if someone said how to solve world hunger, a bot would say kill 10 million people, and that would be a good answer, right?
It is a way to solve it.
It's a frictionless solution. And so I'm going to stick with this line of thought for the last question, but shift is friction as a design choice to friction as a governance choice. In complex systems like supply chains, electrical grids, large tech platforms, some friction shows up as rules, buffers, redundancy, checks, guardrails. It slows things down. It can also prevent catastrophic failure. What's your framework for deciding where to add those guardrails and slack, even if it makes the system more friction, less efficient and with more friction. How do you tell the difference between healthy friction that provides resilience and dead friction that just wastes time and energy?
I think it goes back to how we were talking before, taking that systems approach. And you have to think of second order consequences, which is something I'm worried that these frictionless processes we're doing now, it's eliminating our ability to think of second order consequences. So you have to sit here and think, this is my process. I need to put this guardrail up here because if I don't, the person operating this machinery could fall in. It might be a 1% chance, but it is not worth risking that 1%. If I remove that guardrail, what might happen? This speeds up, but this might happen. It's
Mhm.
really thinking of
Consequences.
the consequences, and I just think we're seeing more and more that there's a lack of thought around consequences other than the immediate. We're doing this right here now because that will move this one needle and that's all I care about. And then, you have 10 other needles that all start breaking. So it's just like with physical friction, you have to assess your system and figure out where is the friction? Where might I accidentally introduce friction if I change this part? And is this friction that is helpful to me? Is it detrimental to me? Is it neutral? And what can I do about these things? And if I do so, what happens next? It's a very engineering approach, but I think we have to do that with social and processes and everything in the workplace as well. I think that's the way to look at things.
So what do you think about the people running our thought processes right now, or running our social, our politics, everything else? They're very frictionless type of people. Either you just go along or they're trying to eliminate it. What is the implications for humanity with no friction?
I think it's very dangerous, and it's the kind of thing that'll keep me up at night. Uh, we need that friction. If someone has a terrible idea, even if it's well intentioned, I'm not going to get into it, but just if someone has a terrible idea, someone needs to be able to speak up and push back and provide a little bit of friction. If we all just want to be frictionless, terrible decisions will keep being made. They will have knock on consequences that we might not be able to undo. We have to be able to develop the skills to have these conversations, to accept that friction is okay. Um, that's a big thing with the chatbots. I worry about the ability of people to actually handle human interactions and conversations when they're not easy. I hear it, even in the workplace sometimes, like, well, I don't want to have that conversation because they're mean. It's like, they're not mean. They're just literally challenging your idea and giving you a different perspective, and you have to have those perspectives or else you just end up risking going down a terrible path that you may not be able to hit the brakes on and reverse.
It affects everything. Like, this is actually has longevity implications, right? When
Yeah.
you have it will affect the human race in a way that, and also no one gets to have sex then, because guess what's the most friction-filled thing
Yes.
is
Yep.
sex.
It's
But I
yep,
guess a lot
something
of them,
tribologists have to study too.
yeah,
Condoms
absolutely.
didn't design themselves.
Yeah, no, they don't. I really appreciate it. Jennifer, this
Thank
is a
you.
wonderful book, and it's so well worth reading, and such an important issue because, as you said, it covers so many parts of our world and is a critically important part of us, and we should reclaim it from the people
Yes.
who are trying to take it away from us. Thank you
Resistance
so
is
much.
progress.
Progress, yeah. Anyway, thank you so
Thank
much.
you.
Today's show was produced by Christian Castro-Russell, Michelle Alloy, Catherine Millsop, Megan Burney, and Kaylin Lynch. Nishat Kurwa is Vox Media's executive producer of podcasts. Special thanks to Catherine Barner. And our theme music is by Trackademics. If you're already following this show, you get a ball bearing. You get a lot of ball bearings. If not, you get to travel with Elon Musk in space, and in space, no one can hear you scream. Thanks for watching. See you on Monday.